Thanks to all the Global NMR organizers for this opportunity to present our work. And very fortunate to be joined by my colleague, Dr. Rovnyak, who is not only an expert in non-uniform sampling and sampling schedules, but an awesome explainer about such things. So today should be a treat for folks who are interested in non-uniform sampling and would like to learn the latest info about how to apply it most effectively. So let's start with some background, all right? So in a multidimensional NMR experiment, we acquire a series of separate one-dimensional measurements. And in the multidimensional pulse sequence, somewhere we have the equivalent of a pair of pulses with an evolution time that's incremented in a systematic way. And we acquire this collection of 1D spectra with these systematic changes, and that gives us a two-dimensional matrix. Now, it's easy to forget, but obvious when you consider it. We're measuring a 1D experiment over and over again, so naturally it has the same signals. The sample is the same, so we measure 1D experiments over and over, and each one of the 1D experiments has the same signals. But because of this systematic adjustment in the pulse sequence, the intensities of those signals are modulated in some way in the indirect dimensions of the measurement. And so if we Fourier transform all the rows of this measurement, that gives us an interferogram, and those signals are being modulated in this indirect dimension, so that if we Fourier transform all the columns of this indirect dimension, we get our nice spectrum. This scheme implies many things that are important to consider. So first of all, as we said, every one-dimensional increment in these multidimensional measurements has the same 1D signals, just modulated in intensity during the course of the experiment. Likewise, in a 3D or 4D, every 2D plane has the same 2D signals in it, but those signals are modulated in that third dimension. And likewise, every 3D cube in a 4-dimensional experiment has the same 3D peaks, but those peaks have their amplitudes modulated in their 4th dimension. So that's one thing to keep in mind. And the other thing to keep in mind is, since we're starting with one-dimensional signals that are modulated in one or more indirect dimensions, even though we acquire a multidimensional matrix, the points in that multidimensional matrix are not independent of each other. So for example, in the case of a two-dimensional signal, we have a one-dimensional signal that gets modulated in the indirect dimension. And so this entire 2D matrix that we acquire for any one given signal, this entire 2D matrix can be described as the product of two one-dimensional functions, which in the time domain are time domain signals. Now, when we Fourier transform all the rows of a matrix like this, we get a similar matrix, our interferogram, and even though it's a two-dimensional matrix, it can still be described exactly as the product of two one-dimensional profiles, but now one of them is a frequency domain profile, and the other is still time domain. And now finally, when we Fourier transform all these columns, we get a spectrum, and likewise, even though it's a two-dimensional matrix, all the information about one signal is contained within two one-dimensional profiles. And now both profiles are frequency domain profiles. When we use a Fourier transform to go between these time domain interferogram and spectral spaces, there's no change in the information content. The time domain data has the same information as the interferogram and the same information as the spectrum. So that's important to keep in mind. And we go through this whole procedure just because a human can identify peaks in a fully transformed spectrum, but not so well in time domain data. So in a sense, this whole procedure of spectral reconstruction is a convenience to allow spectral data to be analyzed visually. Now, in our multidimensional experiment, we acquire a series of 1D measurements as we've described. And so the overall measurement time of the multidimensional experiment depends on how many one-dimensional increments that we measure. And in our conventional scheme, we are systematically incrementing something during the course of the pulse sequence. One simple-minded way to reduce measurement time is simply to skip some fraction of the measurements. And we can skip the measurements according to different patterns that we'll talk about in detail, especially when our colleague Professor Rovnyak is up speaking. And so we can have a sampling schedule that can be uniformly random. We can have a sampling schedule that's very dense at the beginning or dense at the end or both. And these will have different properties in terms of the information that they capture and the kind of spectrum that they can reconstruct. The challenge is, however, that when we Fourier transform all the rows of such non-uniformly sampled data to get an interferogram, the interferogram has gaps in it in the places where we skip the 1D measurement, so that when we Fourier transform this indirect dimension, we get a spectrum that has sampling artifacts. Now, to understand what happens and why this is valuable to do, it's good to remember that the resolution achievable in the reconstruction depends on the length of the evolution time. In other words, the distance in time between the first point that we acquire and the last point that we acquire. And to understand why this is so, we can see it graphically by considering two signals that are very close together in frequency. So here's the signals in blue and red in the time domain, and an excerpt of the corresponding spectrum in the frequency domain. So when we measure time points over a short interval, it's very difficult to tell the difference between two frequencies that are close together. But as we sample more and more points, it becomes easier and easier to distinguish the difference between these two frequencies, and in the corresponding spectrum, the lines get narrower. So again, it's easier to tell the difference between the two corresponding frequencies. So non-uniform sampling lets us take a limited number of samples and distribute it over a larger time course, thus giving us data that reduces measurement time, but retains the maximum sensitivity that could be achieved by the measurement. Now, to understand how this works, it's useful to discuss the Fourier transform. And the form that we use the Fourier transform in NMR is the discrete Fourier transform, where we have some time domain data, a little x of t that we'd like to Fourier transform. And to do that, we multiply our time domain data by a Fourier term and add up all the points in that product, and that gives us 1 point in the corresponding spectrum. These Fourier terms are complex exponentials that boil down to a real part that's a cosine term and an imaginary part that's a negative sine term. So how does all this work? Well, it means that for every Fourier term that we have in the transform, it corresponds to one particular frequency position in the corresponding spectrum. And so let's look at the actual mechanism of the Fourier transform. So we'll step through our different Fourier terms and multiply them with our time domain data, and that'll form a product, and then we'll sum over all the points in the product. All of this happens with real and imaginary data, but for clarity, I'm only going to draw the real parts of the Fourier transform. So we start with our time domain data that we want to Fourier transform. We have one of the Fourier terms. We multiply the Fourier term by the time domain data, and that gives us a product. And we do that for all the different Fourier terms, step through them. In each case, we get a product. Now, the Fourier terms are sinusoids, and our NMR signals are sinusoids. And when you multiply two different sinusoids together, the product that you get has exactly balanced amounts of positive and negative intensities. So when you add them all up, you get something that's more or less zero. And as we step through the different Fourier terms, it's only in the circumstances where the Fourier term matches one of the frequencies in the time domain data that we get a product that's predominantly positive or predominantly negative, so that when we add up all the points in this product, we get a peak in the corresponding spectrum. So in a sense, the Fourier transform is just a systematic matching of frequencies in the Fourier terms with frequencies in the time domain data. So this is what it looks like in the perfect case of a continuous, non-decaying time domain signal. But in practice, of course, we can only measure data over a limited amount of time. And so in the typical indirect dimension of a multidimensional experiment, we have truncated data. And when we try to Fourier transform truncated data, we multiply our Fourier term by our truncated data, and that forms a product which is also truncated. And because the product is truncated, when we add up all the points, there's no longer perfect cancellation between the positive parts and the negative parts. So we get a spectrum that has these artifacts. And also, the signals are artificially broad. All right. And the artifacts oscillate. And the reason that they oscillate is because sometimes the truncation will fall in the middle of a particular sine wave. Sometimes it'll fall at the zero crossing, and it'll just systematically move through different fractions of a cycle and cause these oscillations. So this is what happens with a conventional sampling schedule. In a non-uniform sampling schedule, instead of truncating the data immediately, we take the same number of samples, but distribute them over a longer acquisition time, right? And so that corresponds to having measured data that has gaps in it that we fill in by zeros. And the same kind of situation applies. If we have data with zeros in them, different gaps, when we multiply them by a particular Fourier term, our corresponding product has gaps. And so when we add up all the points, we no longer get perfect cancellation of the positive and negative parts. So we still get these artifacts, but since the gaps are in random places, these artifacts seem to have a random form. But look what happens. We also get a nice narrow peak. And so both of these cases are sampling schedules. Our truncated time domain data is a uniform schedule. Our non-uniformly sampled data is, of course, a non-uniform sample. The truncated time domain sampling schedule gives us artificially broad signals with regular truncation artifacts that get smaller as they travel away from the peak. But in non-uniform sampling cases, we get nice narrow peaks, but these crazy artifacts that look like random noise. They're not random noise. They are determined specifically by the pattern of points that we kept and skipped. All right. So we'd like to be able to retain this advantage of nice narrow peaks without these artifacts. And so how do we do that? In order to do that, we have to do the equivalent of filling in the missing points. And any procedure that we use to fill in missing points in the data, either directly or indirectly, can also be used to extrapolate and add additional points at the end of the data. So whatever mathematical tool that we use to fill in the blanks in the interior of the data, we can also use that mathematical tool to add synthetic points at the end of the data. So this is non-uniform sampling interpolation, and this is non-uniform sampling extrapolation. And because we have data now that extend over a larger duration, we've increased the apparent resolution of the result. How do we generate a reconstruction from this non-uniformly sampled data? We can take advantage of the fact that the artifacts, the reconstruction artifacts that we see in a Fourier transform are proportional to the size of the peaks. All the peaks have the same artifacts. The big peaks have big versions of the artifacts. The small peaks have correspondingly smaller versions of these artifacts. And so we can start with an ordinary Fourier transform of our non-uniformly sampled data that has these crazy looking noise-like artifacts. And we can choose a threshold that we know is much larger than the largest possible reconstruction artifacts in the spectrum. And we can take a little bit of intensity from the signals that are above this threshold and move them into a secondary spectrum. And then choose a new lower threshold, inverse transform the data back into the time domain, and reset any parts of the data that were skipped in the original non-uniform sampling schedule back to 0, and Fourier transform them back into the frequency domain. Choose a new lower threshold and repeat this procedure. So we gradually transfer intensities from the tops of the largest signal and accumulate them into a spectrum. And as the original signals get smaller and smaller, the corresponding artifacts get smaller too. And at the end, whatever residual is left, we can add into a final result. So we can iteratively get a nice spectrum without reconstruction artifacts. This method is called iterative soft thresholding. And it works really well. So here's a small molecule case, a bile acid. Looks here, and this is data from our colleagues at Pfizer. So if we can measure 1,000 increments in the indirect dimension, we get a nicely resolved spectrum. And if we look, say, at this little pair of peaks here, they're nicely resolved if we measure 1,000 increments. If we only measure 128 increments, we greatly compromise the resolution in this indirect dimension. And so, for example, if we look at this same pair of peaks, they're not resolved anymore. So this measurement takes 4 hours. This measurement takes half an hour. In a pharmaceutical environment, this would mean that this measurement has to be postponed to a night queue. And so an analyst would not get a result until the following day, whereas a measurement that only takes a half an hour could be done more or less immediately. So in a pharma context, that's important. So here's our conventional data that takes 4 hours. If we take the same 64 samples in the short measurement example and spread them out over a long duration with a non-uniformly sampled schedule and use IST reconstruction with this extrapolation method, we can actually get a spectrum that has better resolution, better apparent resolution than the long fully sampled measurement. And we can use different sampling schedules. So here's one that's weighted at the end, and we get pretty much the same kind of result. Here's one that's only weighted at the beginning. And so why are these cases all giving us good results? Well, in this particular example, if you look at the signal in the indirect dimension of our molecule, it doesn't decay much over the course of this particular measurement. And so there's no particular advantage in acquiring lots of points at the beginning compared to points at the end, because the signal height is pretty much the same everywhere. And that's a kind of important message that in routine cases, especially with signals that don't decay too much, there's not a large difference between different sampling schedules. However, something that's critical to consider is the nature of the data. So whatever kind of non-uniform sampling schedule you assemble, it has to have two properties. It has to capture enough signal to get above whatever noise there is, and it has to have enough samples to describe all of the signals in the data. So in other words, the effectiveness of non-uniform sampling depends on the number of signals in the data, and as we'll see, it also depends on how they are distributed. All right? And here's a case that's based on a 3D NOE spectrum. And we have a model of all the signals in the proton-carbon plane of this 3D data. In the fully sampled spectrum, we can see 378 peaks, and this is synthetic data that mimics the actual spectral data, and it has distortions added into it to make it more realistic. And so we can take subsets of these different cases, half the number of peaks and so on, and use the same non-uniform sampling schedules to reconstruct all of these data sets, and then keep track of how the results change as we reduce the number of increments. So at 100% sampling, all of these cases look good. At 95%, 90, 85, 80, everything looks quite good in all of these cases. Now we get down to 50% sampling, we can start to see artifacts in the spectrum that has 378 peaks. But the spectrum with 180 peaks still looks good. By 30%, we start to see substantial artifacts. And now at 25%, we start to see artifacts here. At 20%, this spectrum with 378 peaks is completely unusable, whereas the spectra with 93 peaks and 18 peaks have been almost completely unaffected. And down at 15%, now this spectrum starts to look bad. At 10%, this spectrum starts to get artifacts. At 5%, all of these three spectra are unusable, but the spectrum with only 18 peaks has most all of its signals still visible. So the number of samples that you need to reconstruct a spectrum depends on the number of peaks there are in the most crowded regions of the spectrum. And we can even make a little formula that tells us to anticipate how many samples we need for regions with the most dense peaks in the spectrum. There's another aspect to this. As we're going to hear in detail from David Rovnyak, the different shapes of sampling schedules have different behaviors. So if we have a uniformly random sampling schedule and we Fourier transform it, we get a result that has uniformly distributed reconstruction artifacts. But if we have any kind of weighting in the sampling schedule, when we Fourier transform it to see the reconstruction artifacts, we will see that in the same way that the sampling schedule changes systematically, we have reconstruction artifacts that change systematically. They are small near their peaks and get larger as they go away from the peaks. And so what this means is sampling schedules like this are going to favor spectra where the peaks are grouped together closely because they're going to be in regions where their mutual reconstruction artifacts are at their smallest. So these sampling schedules affect the reconstruction quality not only on the basis of the number of signals that are in the spectrum, but on the basis of how those signals are distributed. Now, that said, all of these methods are relatively easy to apply, and since we can use them to extrapolate data, we can use them on conventional NMR as an alternative to linear prediction. And in the case of non-uniformly sampled data, we can use them in different ways and get beautifully resolved results. In this case, we can take conventional data and resample it according to any sampling schedule to see how non-uniform sampling will affect a particular data set. And that's a very valuable tool. And I'm going to talk about now a new way to evaluate non-uniformly sampled data without applying Fourier processing to the indirect dimensions. And that's the work of Micah Smith, a computational biologist here at IBBR, who's developed a Python version of NMR pipes pipeline processing. And the first new function implemented it is a function called DECO, a function for linear decomposition of spectral data. So let's return to the idea that we discussed, that in a 2D plane, any 2D plane in a 3D or 4D signal is a linear combination of the same 2D signals. So in a 3D interferogram, all of the 2D planes are composed of the same 2D signals that are modulated, in this case by a time domain expression in that third dimension. And that still holds true if we Fourier transform the first two dimensions of this 3D data. So this is for a 3D or 4D measurement, but also this holds true for many kinds of pseudo 3D measurements. So for example, in a relaxation series, every 2D plane has the same 2D signals in it, just modulated in this case by some relaxation expression. And in the case of a CEST experiment, every 2D plane has the same signals, but they vary in accordance to some kind of pseudo CEST spectrum in the third dimension. And so if we know all of the signals in a 2D plane, say a reference 2D plane or a projection, we can analyze the indirect dimension of the data by linear decomposition, because if we know where all the 2D signals are, we can analyze any given 2D plane to determine the coefficients of the linear combination that describe that plane. And when we pull out these coefficients, they tell us how the signal evolves in the indirect dimension. And because the information content is the same in a spectrum or an interferogram, when we extract these evolutions, they are the same values if we extract them from an interferogram as they are if we extract them from Fourier transformed planes. And so what that means is that we can extract data from a spectrum regardless of whether the indirect dimensions have been Fourier transformed. And this holds true for both conventional and non-uniformly sampled data. So how does that work? Here's a 2D case. In this 2D case, we have our measured spectrum, which is here, and its interferogram looks like this. So we can build a basis set. This is a synthetic model of the spectral data. So here's the spectral data. Here's our synthetic model. Here is, in this case, the residual, which basically just doesn't account for the little reconstruction artifacts in the spectrum. So this synthetic spectrum has a corresponding interferogram. We can consider all the signals in this interferogram separately. So in the same way that we know that any 2D plane we want to analyze is a linear combination of all of these signals in the basis set, the interferogram is also a linear combination of signals. But in this case, the basis set is expressed as a spectrum. In this case, it's expressed as an interferogram. But in both of these cases, when we extract linear coefficients, we get the same values, whether our basis set is a spectrum or it is an interferogram. So what does that allow us to do? It allows us to pull out evolutions of signals. So for example, in this relaxation experiment, we can pull out the intensities from non-uniformly sampled data without reconstruction about as effectively as we can with the fully sampled data. And here are the relaxation curve intensities extracted from a fully sampled spectrum compared to a spectrum that's sampled at 1/8 density. So this is one thing that we can do with the linear decomposition. But another thing that we can do, which is interesting and useful, is use it to evaluate different sampling schedules, and we can do it independently of reconstruction. So in this example, we have spectral data that's been approximated by a 2D model, and we can convert that 2D model to an interferogram and use it to fit the experimental interferogram to extract the intensities in the indirect dimension. And we can try that for different sampling schedules. So this is a case where we only sample the first increment and the last increment. And so the parts in gray here are the parts that are skipped by the sampling schedule. And if we only sample 2 increments, we get a pretty bad representation of the spectrum. So it doesn't match very well. This graph shows how well our linear decomposition model matches the experimental data. And we'll see as we add more and more samples, we get a better and better description of the data by using this linear combination of basis sets. And so what this tells us is how many increments that we need to describe our data as well as we want to. And the other thing it tells us is for a particular sampling schedule, by looking at this residual, we can see which parts of the spectrum are going to be problems for a particular sampling schedule. So not only can we evaluate sampling schedules, but we can custom tailor them to the specific arrangement of peaks that we have in the corresponding spectrum. So that's the result, and that's another nice tool that we have to be able to work with non-uniform sampling in the most effective way. And so I'll just reinforce a few points before we turn things over to our colleague, Dr. Rovnyak. The important points that we've discussed: one is that the effectiveness of a NUS application, which means choice of the sampling schedule, acquisition parameters, and reconstruction method altogether, the effectiveness of a scheme depends on the number and distribution of signals, as well as the things that you would expect, like signal to noise, dynamic range, and how broad the peaks are. And we've also shown that linear decomposition gives us an interesting way to extract information from non-uniformly sampled data without reconstructing the indirect dimensions. So those are the important details that I wanted to discuss. Thank you for your attention. I'm eager now to hear the description that Dr. Rovnyak has for us. So thanks very much. Look forward to your questions at the ends of these lectures.
Many thanks. That's fantastic. Let me just take a moment to pause and thank Dr. Frank Delaglio for a masterclass in NUS. I'm going to go back and I'm going to rewatch this video over and over and over again. You also stole my first line. Through my journeys through NMR and sampling in NUS, I have always been extremely grateful for the clarity that you bring to sampling and processing. And so I just want to say thank you for all of that. I will try to now model some semblance of that degree of clarity and explore NUS scheduling as well from very related and similar perspectives. And this is the prompt: what is a good schedule and how do I know? And before we dive into that, I just want to make sure to share a variety of thanks for funding for the NSF, who is actually helping to support us in some of this fundamental work. We are grateful for the very unique vendor space in NMR spectroscopy, and we work with Mesterlab, and then more recently with Jail as well. And also, you're going to see NMR Box come into this at the end, and grateful to George Weatherby there, who helped make that possible. You're not seeing double or triple or whatever. You may see some familiar names. It's my privilege to be able to work with some family members in this work. And so you're going to hear recent work as well from fantastic recent MS student Lucy Colin, and also from Henry, who presented some of this work recently at ENC as well. And that's Bucknell. It's a great place to do NMR. And if you're ever through, we would love to see you all there. So I would direct you to a recent review that I put together, and I just want to thank Bill Price for helping to make that possible, where I want to call out a quick quote at the end of that review. The understanding and implementation of sound sampling principles has improved a great deal. From the seeming complexity, improved generators and schedules have emerged that can be used easily by all. That is, I think that many of us who work in NUS are aware that sometimes NUS can appear very complex and have a lot of associated variables and decisions to make. And part of this presentation and part of our work in general is to try to take some of that out of the process and model how people develop successful NUS strategies for NMR spectroscopy. So for this second part, I'm going to be reinforcing some of the things that you heard in that fantastic presentation, and also sharing some of the frameworks that you can bring to thinking about designing NUS strategies. And that will include a new scheduler that we've recently released. So again, why NUS? I think that's been really firmly established, and I've set up this slide as foreshadowing. I want to revisit this at the end. You might use it for time savings, for improving resolution, and there's even some opportunities to have modest improvements in sensitivity when you have short T2s, and you can weight your sampling to very early times to take advantage of those short T2s. It is important to recognize that you can have weighted or unweighted non-uniform sampling. So here's an example of a uniformly sampled signal. Here's an example of weighted non-uniform sampling, where you see more data points are taken earlier on, where the signal is more intense. This goes back to fantastic pioneering work by Barna and Lowy in the 80s. And so we call that on-grid weighted because we selected data points from the grid of uniform points, which we often call the Nyquist grid. You can also have random unweighted, and this is also something that we've seen in the previous presentation, and we'll explore a little bit more here as well. So those are some of the initial concepts. And I would refer people back to, again, that review article, which has a large section on terminology that hopefully makes the terminology a little bit more approachable. Generally, we want to think about the number of dimensions in which we're using non-uniform sampling. So here are some straightforward examples of schedules that can be used in each dimension. And one of the things that you might notice is that you can have different weightings of those schedules. Some of these schedules are weighted to earlier times more than others. But what I really want to delve into today is, what is a good schedule and how do I know? That's our prompt, and we're going to try to see if we can, the degree to which that we can address this. And over the years, I've had the luxury to really think deeply about the schedule itself, and that's been the obsession of our group for many, many years. What are the fundamental properties of the schedule itself that we should be paying attention to? And I'm going to take us through each of these. And even though this may seem like a lot at first, I think they start to coalesce and you start to see the connections between them. Also, I want to pause and just point out that these are conditions that have come about from an enormous community of researchers and pioneering work, and all of the maturation of NUS that has occurred from dozens and dozens of labs. And it's not possible to properly thank all of them here and recognize all of their extraordinary contributions here, but this is the product of an enormous community effort. These are broadly relevant throughout NDNMR, but I like to point out that 1D NUS schedules experience these criteria strongly, and ultra-high fields experience these criteria strongly. So let's explore these and see what they mean for us. So we've already heard about this. You want to have sufficient samples in order to detect the number of signals that you expect in your spectrum. And it's worth just pausing to realize that every peak represents three things that you want to know. You want to know its line width, frequency, and area. And the number of parameters that you might have to extract can be quite large. If you expect something like 8 signals in a given slice of your 2D NMR spectrum, you're trying to now recover 24 parameters from one slice of your spectrum. And so some really fantastic work that I encourage people to look at is from Nichols and Delaglio, very nice work on NOSI and NUS, where they actually devised good metrics for whether or not you're following in a regime of good or poor reconstructions. So want to look a little bit more at the three concepts that are related. Probability density, this is the weighting of your sampling schedule. And we'll then proceed to think about gaps and tessellation a little bit more as well. So generally, probability density, PDF function is telling you where you're taking your samples, and it can be unweighted, and that's just uniform sampling, for example, is unweighted, but you can also have random unweighted, as we've seen. You can also have something that's weighted, for example, this decreasing dashed PDF that you see. And there are examples of both. There's some variations. For example, here's the random unweighted. That's still unweighted in principle. In practice, as soon as you go to random unweighted sampling, you do have to recognize that the actual PDF there is not necessarily perfectly constant. You're now attempting to approximate the PDF with your samples. You can actually instead do uniform sampling, but instead change the number of transients or scans per sample, and that's called NUWS. That continues to be explored and be of interest, for example, the work of the Mueller group and others. And something that I think still deserves a little bit more of a look is that you could actually consider combining both, doing both NUS and NUWS at the same time. And it's also worth pointing out that algorithm matters. For example, it's not just what the weighting is, but it's how you attempt to achieve that weighting. So here are two cases where they're both exponentially weighted with the same exponentially decaying factor, but one was done according to a random algorithm, one was done according to a deterministic algorithm. So even though these attempt to have the same weighting, they are remarkably different sampling schedules. So algorithm matters, not just the weighting function itself. Different weighting functions give you different distributions of points and help to bring in some of the gap management and tessellation concepts. So here are some common PDFs on the left-hand side. They include exponential PDFs, a sinusoidal PDF that we like, also the very well-known Poisson gap PDF. By the way, I tend to say PG2, but that's what most people know as PG. And just to emphasize that these are not as different as they initially look, the normalized display on the right shows a more faithful comparison of the probability density functions, where you see that they're actually more similar than they might first appear. When you're comparing these and when you're thinking about making choices, notice that Poisson gap tends to take samples very densely at the beginning and then more evenly for the rest of the schedule. On the other hand, some of the other PDFs tend to take more samples around the middle or around the roughly 1/3 of the sampling schedule. And you can see examples of them shown below. When you're looking at evaluating different probability densities and you're thinking about which ones work for you, here's a set of examples on ubiquitin that show a Poisson gap, a quantile, and a random unweighted case, where in this case, this was highlighted some of the pitfalls of random algorithms in sampling schedules. Particularly, the random schedule ended up developing some very large gaps. And in fact, in the reconstruction, some very undesirable aspects happened in these reconstructions, including some large extra peaks, a lot of noise, a lot of artifactual noise. And I actually very much like that phrase, noise-like artifacts. That's really a good phrase to use here. Now, in showing this example, I want to be cautious. I don't want to bias people against random unweighted. but rather to show some of the issues that we have to think about when we're choosing sampling schedules. We also heard about the point spread function, and this is great. I get to skim over this a little bit more quickly. It's the DFT of the sampling schedule. It convolves with the true signal. And so it has a couple of aspects that we want to be aware of. We want to be aware of the central peak, which is the good part of the point spread function. But then we have these noise-like artifacts that complicate spectral interpretation and reconstruction. And the goal is to suppress them as much as possible so that they don't interfere with our analysis of the data. One of the tempting things about a point spread function is to actually look at the peak to side lobe ratio, the peak indicated by the asterisk and the side lobe indicated by the hashtag or pound, depending on your generation. And that ratio might at first seem compelling. It tells you about the magnitude of the noise-like artifacts in the point spread function. However, it's turning out that that's not as helpful a metric as first thought. In fact, some recent works are cautioning that this peak to side lobe ratio, while it's interesting and may still have some value, does not score schedules well. Now, we are going to actually revisit that, and I'm going to cast that in a different light. I think this is an aspect of schedule design that really deserves a little bit more attention, that we want to think about the scientist at the spectrometer thinking about how they're going to implement NUS. Again, some of our lab's thinking over many years has taken more of a generalist approach. How can we broaden the adoption of NUS? And we know that people want to know what their NUS is doing. When you see Poisson gap, what does that mean? When you see quantile, what does that mean? And so forth. And I think there's some good that we have these named approaches that bring some clarity to what we're doing. But nonetheless, I think we still want to build more intuition with these methods. Also, we have a challenge. As we've learned to develop better sampling schedules, the number of folks, including us, have worked on sophisticated schedule filtering methods that add some complexity. And so if I was to have maybe one risky comment here, is that we may reach a point where we may not be able to talk about the entire complicated procedure that goes into generating a sampling schedule. And we also have to think a little bit more about reporting. Reporting is tricky because generators may have more parameters than you first think when you generate a schedule, and it may be easy to overlook certain parameters. It is safest and easiest to put the schedule in SI, and that's something that I'm a big fan of, and I encourage everybody here who's using or thinking of using NUS to do that. I'd like to briefly mention, again, the low variance concept that just came up. This was discussed very nicely by Zambrello and Schuyler recently, that different schedules yield the same spectral information. This is actually a really reassuring concept. This is telling us that there is a robustness to NUS in general, that yes, there are schedules that perform better and worse than others, but overall, many modern schedulers today, I think, have achieved that low variance criterion. Reproducibility is related, but you might notice some distinct concepts here. So reproducibility can be seed independent or low seed dependence. There are some scoring systems to help us with this how do I know part of the process. And granted, these are being used more often by specialists, but nonetheless, I chose two that are experiencing active development. I wanted to mention NUS score from Aoto and Wright that's recently been revisited in 2025 by Darling et al. And I wanted to mention the IROC method by Zambrello and Schuyler, which again has been revisited recently in 2025. Both of these seek to help us score and feel more confident in the sampling schedules that we're using. Currently, they're used more behind the scenes in the development of schedules. But I think these are showing good promise for scoring, and I think we should continue to work on scoring systems for NUS. One of the things I want to pay special attention to is a well-known problem in NUS, which is that it breaks Nyquist. So aliasing within the spectral window is something that has to be considered. Two foundational papers are really worth calling out here if you're interested to look into that more. Then fantastic work in 2009 looking at aliasing, where it was noticed that if you include short uniform bursts, you can really disrupt aliasing, that you're essentially locking in some of the Nyquist frequency that way. And this is something that really got us interested. We were starting to look at what we saw was incomplete deconvolution of the point spread function. You see this noise arising, blue shifted noise, as we've heard about, arising at the edges of the spectrum. And we started to realize that if we just lock in a little bit of Nyquist by linearizing the initial portion of the spectrum, that we can make great inroads into decreasing that sampling noise. And this is a case where, again, the PSF is not necessarily directly useful. If you compare the PSFs of those two schedules, it would be difficult to see that one would perform any better than the other. And so this is part of the complexity behind using the PSF. It tells us a lot about our reconstruction challenge, but sometimes it masks some of the information we want to know. And so that takes us into decoherence, and that's consumed us for a few years. So here's a related example of an HSQC that actually has an intentionally very, very bad subharmonic sequence in the sampling schedule that's every other point. So this portion only has half the spectral window of our actual grid, and it's actually given us mirrored peaks. And if we just go through and break up that pattern, we eliminate those alias peaks, and we nearly eliminate those alias peaks. They're present as artifactual noise-like appearance right now. And we generated some metrics of decoherence that you can see here to help grade that. And so we started to really come to believe that treating pattern sampling is something that should be done intentionally. And it should be hands-free, it should be general, theory-based. And we started to realize also that it should look at patterns both locally and globally, and it should also honor user choices. We don't want this to be something that disrupts user choices. So this is where Henry entered in with some really fresh thinking to develop some new algorithms and bring some new theory into this to try to make schedules rigorously decoherent and in a way that can still be done at the spectrometer, and in fact in the background. So first was to look at local patterns and to use something called the 2-Morse sequence. Really neat sequence. It's an intrinsically decoherent binary sequence, and it has a very useful property. It does not contain triples. So it will not contain, for example, 1 0 1 0 1 0. That's a triple of 1 0. And he devised a algorithm that performs 2-point swaps. So this is designed to be gentle and to treat schedules locally, to go and fix regions that needed the help. But this is not enough. This is only going to address local issues. And so the next thing that he worked on was a way to address global issues. And here he turned to the point spread function. And as we know, the point spread function is tricky to use. The peak to side lobe ratio is a little tricky, and sometimes its flaws are masked, as we saw in a recent example. And so what he came up with here was an inverse thresholding approach. It's outlined in this schematic. I don't think we need to go into too much of it in the interest of time, but one of the key things is this focuses on more than just the peak to side lobe ratio. This actually has a smoothing effect, and so you can see the example here. And it's, again, gentle, and it has a very unique stop criterion that Henry came up with that I don't have time to show you, but it's really an outstanding stopping criterion. And it has the effect of tamping down the peak to side lobe ratio iteratively and presenting a very smoothed point spread function. So to see these things in action, if we take a base schedule that shows some large artifacts, if you just do the TM filter, some of them go away, but some of them remain. If you add on the PSF polisher, more of them go away, and you get a spectrum that I think generally has the largest artifacts reduced. Now, it doesn't mean that artifacts are eliminated. This is not a panacea at this level of sparsity for sampling and at this level of complexity. This is an HMBC. You expect to still see artifactual noise, but this certainly takes out the larger artifacts and makes these spectra more reliable, we think. Poisson gap is helpful for this because we can use random seeds and do a lot of tests. By the way, we use the acronym TMPF. So the idea is this can be applied to any schedule, any base schedule, including Poisson gap, as well as our own quantile scheduler. And just in a number of examples, we see a reduction in the larger artifacts. So this is doing a good job of taking larger artifacts out. Just to kind of illustrate what it's doing, if you take an initial schedule like the perfect repeat below, which is an excerpt of a schedule, actually, pardon me, that's important. The PSF polisher by itself focuses on global issues. So it sees something's a little wrong, but it only fixes one point. The TM filter immediately recognizes the issue and fixes it. And then if we apply them in series, it takes the result of the TM filter, contextualizes it with the rest of the schedule, and makes a couple more tweaks, and we have our final excerpt. Overall, the goal of this method is something more reliable. That is, we don't think this is optimal for a lot of reasons. Optimal is a loaded word. Different people have different requirements for what optimal is. There's also a risk of over-optimizing schedules for specific conditions. And also, we do think that there still remain interesting questions. How much decoherence is enough? And so we hope you'll tune in to see us tackle some of those. We're now calling this USCHED. This replaces QSCHED, which some of you may know about. QSCHED will still be around, don't worry. There's a website for QSCHED as well. We can send you schedules, but this is available now on NMR Box, and look for future developments. So to come full circle, and I see it's noon, so this is good. I will finish up, don't worry. I'm going to give you a generalist overview where I'm not considering the NOE. The NOE is a particularly demanding experiment that generally needs bespoke solutions. Generally, ask what you want NUS to do for you. Do you want a lower sample number and coverage to save time? Then do that. Do you want higher resolution? Do you want to improve sensitivity? I won't repeat these. I think you can read these and get the rough idea of what these entail. And generally, this models the mindset that I bring to situations where I need to design an NUS strategy for a particular spectroscopic problem. The suggested workflow overall: identify your samples and experiments, conduct trials, and switch to research samples. If you're new to NUS, I urge people to start with 50% NUS. That's extremely safe. You build your confidence with it. Almost regardless of your Nyquist grid, 50% will work. So 128 out of 256 or 512 out of 1024 and so on. This is likely to be safe. Switch to lower coverage with PG or quantiles. And again, I don't want to bias people against sparse, against random unweighted, but when random unweighted gets sparse, you do want to exercise caution. That's where we do identify being careful. And finally, try out different reconstructions. And if you want to see what USCHED looks on NMR Box, it's ready to roll. You just type in USCHED, it prompts you, gives you feedback. It will help you make choices. It will show you your schedule. It does a lot of neat things for you. And so you can, we invite you to play with that as you like. So I think that wraps up the comments that I made. And now we look forward to tackling any questions you may have. Thank you so much.
Thank you so much for such a wonderful talk. We do have a question in the chat already. So the first question is a little long. I'll read out, but you can also look at a chat so that make sure it's accurate. So the first question is, if people need to add up the FIDs of several experiments with the same setup to boost signal-to-noise ratio, is there a way to set up the NUS so that the FIDs are addable? Or is it not feasible to use NUS if you need to add up separate experiments, since most sampling are random?
Okay, sorry.
Okay. Do you want to answer, Dave? Or
I think I want to think about that a little bit more. Do you want to dive in first?
Sure. Yes, I'll make an attempt. So, without considering NUS, remember that the information in the time domain is the same as the information in the frequency domain. So, from a kind of theoretical point of view, you can add things together in the time domain or add things together in the frequency domain and get the same kind of result. However, in those circumstances, you have to be careful that the things that you add together have the same phase, or the signals will potentially cancel. So we're going to assume that whatever it is that you're doing, if you're going to add together data sets, they all have exactly the same phases. Now, if you add two different non-uniformly sampled spectra or time domain data sets, that's completely fine to do, but you'll get a new sampling schedule that corresponds to that, right? And there may be certain cases where the same increment was measured in both of those schedules. That's perfectly fine, but you also have to account for it when you convert and process the data. And David Rovnyak talked about this a little bit in terms of the types of sampling schedules where we vary the number of scans from one point to another. So adding together different NUS data sets is kind of the equivalent of a sampling schedule that's like that, where you potentially vary the number of scans.
I think that's perfect. I don't have anything to add.
All righty.
Yeah.
Thanks for that. Nice questions.
Cool. Please just type your questions in the Q&A, and while people are typing the question, I guess I can jump in and ask one. So I have one question for Frank. So David have explained very details about how to scheduling the experiments, and I have one question about the NUS restriction. So you kind of track the peak with certain threshold. So I wonder if the value of threshold in each step matters the accuracy and efficiency of the NUS restriction. If so, how can you decide what number of the threshold you should choose?
In practice, you never have to choose these interactively. Okay, so once you know the sampling schedule, the Fourier transform of that sampling schedule tells you what the artifacts look like. So before you do any reconstruction, we already know how big the largest artifacts can be. And so we can always choose a threshold that's guaranteed to be larger than any of the largest artifacts.
Thank you so much.
And then correspondingly, we know that if we know the noise level of the data, there's a time at which the remaining artifacts during, say, an IST reconstruction get as small as the thermal noise in the data. So that's what tells us how to stop the iterations, that we've described enough of the experimental data.
I think returning to the initial question briefly, one thing maybe I'm not interpreting the question correctly, but if you had two different NUS acquisitions and you're thinking about combining them, if they have the same schedule, that's a little bit more straightforward, and assuming they were acquired under equivalent conditions that you don't have to worry about issues like phase, like Frank said, then I think they can co-add them and you preserve the schedule. If you had two different NUS acquisitions with two different schedules, then indeed that could get tricky, because when you merge the schedules, you may find that certain sample times are the same and certain ones are not. And so you run into that case where you will have both an NUS aspect to your schedule and you'll have an NUWS aspect to your schedule. And so you will have the combination of the two if that happens to be the case. And then it's a matter of whether or not that's currently supported in your given software.
Sounds great. Thank you so much. I think I saw one person raise his hands, but it's now down. Oh, we have another question in the chat. So the third question is, are there scenarios where it's better to oversample data points, say 2 times the phase cycle, instead of doubling the amount of NUS points?
I think I'll jump in on this one. I think it depends. I'm going to go back to my second to last slide. I think it depends on what you want to get out of NUS. There can be reasons to make either choice in principle, and I hate to sound like that's waffling, and we can delve into that more. But I think it depends on what you want to get out of NUS, for example. So if you say take 2 times the phase cycle, so if I understand that correctly, you're proposing doubling the number of scans per sampled evolution time. Then that sounds like you might be doing weighted NUS, and you might be trying to improve your sensitivity a little bit and trying to favor the current sampling schedule. On the other hand, if you double the amount of NUS points, maybe that tells me that you're worried about quantification, and maybe you're going to be developing a protocol to be gentler on your NUS and do more quantifications. So they take you in different directions, depending on what you want to get out of NUS.
I will add again to keep in mind the number of signals and their distribution. Okay, so if you have a spectrum that only has 1 peak, it's not an advantage to acquire 1,000 increments to identify and characterize that peak. So there's a point at which you have enough increments to describe the signals there, and everything else that you can do, it just increases the signal to noise of the measurement. So if that's what you need, once you get up to that critical number of samples, you can just measure more scans instead. And I think in a lot of cases, this is an advantage because most of these reconstruction methods involve Fourier transform steps. It's convenient if you have strong signals to be able to work with in order to do iterative types of spectral processing, which are worse if you have underlying signals that are tiny compared to the random noise.
Sounds great.
I might take advantage of this to just comment on a couple of things that are tangentially related. That there are interesting ideas that have been explored out there. For example, when I first saw the word oversample, I thought something else. You can also oversample in terms of sampling from a finer Nyquist grid so that your effective spectral width is larger. You can push sampling artifacts further outside of your intended spectral window that way. And that's been considered. It hasn't taken off yet, but that's been considered and worth looking at.